Hi, hello friends, welcome to my YouTube channel. Thank you for your views and comments and subscriptions. Now we would like to discuss the Aptransco 2012 EE electrical solutions. Now I am taking a subject which is very famous and having more weightage in our EE exam preparation. So power system. So we'll take the first question here. The first question is a 500 MVA 11 kV synchronous generator has 0.2 per unit synchronous reactance. The per unit synchronous reactance on the base values of 100 MVA 20 and 22 kV. So here we are having two values here. So first one is alternate is 500 MVA and 11 kV. It is having a per unit reactance of how much? 0.2 per unit. Now what we need to find, we are having another base values, so that means we are changing the values. Now the new base value is 100 MVA and 22 kV. So these are new values and these are old values. Now we have the formula. What is the formula? The x per unit new is equal to x per unit old value into the MVA value of new generator, a new value, divided by MVA old into the voltage rating, so in kilovolts kV old value divided by kV new. By substituting these values in this formula we'll get the answer. So what is x per unit old? So it is already 0.2. We already know 0.2 into what is the MVA new? So MVA new is 100 divided by MVA old is 500 into what is the kV old? So old one is 11 kV. Sorry, I forgot here. So it is square here. So 11 divided by 22 whole square is nothing but 0.2 into 100 divided by 500 into 4. So it is nothing but 0.01 per unit. The answer is B. So it is having no units. So 0.01 is the answer. Next question. The next question, for a fault at the terminals of a synchronous generator, the fault current is maximum for a fault. Which fault here? So the option here is, it's a three-phase fault. So the short circuit MVA is nothing but it's a base MVA. So let me correct here. So it is base MVA divided by reactance in per unit. So in alternator we are having three reactance. During the fault condition we have X2 double dash, which is nothing but subtransient reactance. So subtransient reactance is very low in case of alternator during the fault condition. So XT double dash is very low value. So when we talk about the formula, when we convert this formula into currents, so we can say short circuit current is nothing but the base current divided by XT double dash. So this value is very low, so that the short circuit current is very high in case of three-phase fault. The next question is, a 100 MVA 11 kV 3-phase 50 Hz 8-pole synchronous generator has an inertia constant H is equal to 4 seconds. The energy stored in the rotor of the generator at the synchronous speed will be. So here in the given data we need to find the energy stored here. So we will go through the formula which says that the H is nothing but inertia constant H is equal to energy stored in megajoules divided by rating of the machine. Okay, so we want energy stored here. So we know H value, we know rating. So what is the formula here directly? So energy stored in megajoules is equal to, the H is 4 into rating of the machine is, it is 100 MVA. So 100 MVA, so that we will get, so 400 MVA is energy stored here. So the answer is B. The next question is, the use of high speed circuit breakers reduces the short circuit current, improves the system stability, decreases system stability, increases the short circuit current. So option is improves the system stability here. So we will take the basics of stability. So accelerating power is nothing but it's a difference between the mechanical or shaft power minus electrical power here. So normally during stability conditions, normal conditions, stability conditions, the accelerating power should be equal to 0. Okay, so here what is happening is, if Pm, the mechanical power, is constant, now the electrical power is varying here. Okay, so during fault conditions what will happen? So during fault conditions, so current, short circuit current will be very high, so that electrical power will be very high. Okay, so when the electrical power is high, the PA will become, so Pm minus P electrical, so this is very high, so the accelerating power become deaccelerating power. So the machine may lose stability. So in order to maintain the stability, some of the electrical power required demand can be removed. So with the help of high speed circuit breakers, so that we can maintain the stability here. So the use of high speed circuit breakers or a high speed governing system, we can improve the transient stability. If they are specifically, we can improve the transient stability. Next question. The next question is, bundle conductors are employed to improve. So bundle conductors are employed to improve the corona performance of the line. So how can we improve the corona performance? So the potential gradient G is inversely proportional to radius of the conductor. If the radius of the conductor is very less, so we can improve the voltage gradient. So corona losses, so is V phase minus V gradient whole square. So if this increases, voltage gradient increases, means total overall corona losses will decrease here. So based on that, we can say the corona performance of the line increases, or corona losses will decreases if we use bundle conductors. Next question. So during a disturbance on a synchronous machine, the rotor swings from A to B, finally settling down to a steady state point at a C in the power angle curve. The speed of the machine during the oscillations is synchronous at points. So we will draw the curve. So power angle curve we will draw first. So here in y-axis we will take the power, and x-axis will take delta, and we will have power angle curve like this, that is in the form of cos theta. Now, so first of all, here the stable point A, and from A to B here, and finally settle down to a point C here in between these 3 points. Now the speed of the machine during the oscillations, so oscillations are very important here when you're making oscillations. So during oscillations, where it will have synchronous speed. The synchronous speed is between B and C only. If you go beyond that one, the speed will become asynchronous speed it will become. So the points are B and C, where the machine oscillate between these 2 points. The machine will try to maintain its synchronous speed. So answer is B and C. The next question, if the reference bus is changed in load flow runs with the same system data, and the power obtained for the reference bus taken as specified P and Q in a later run, the system losses. So first thing is, we are taking a slack bus here. So let me take a slack, or we can also call it as a reference bus. So can you recall what are the known quantities in slack bus? So it is nothing but V at an angle delta. These are 2 known quantities. What are the unknown quantities? P and Q are unknown. Okay, now next what is happening here is, so later we choose another bus, that this is the same reference bus, but the quantities specified are PQ are known. So what are the unknown quantities here? V at an angle delta. So voltage and delta will not know here. So the losses will not change. So answer will be the losses will not change, but the complex bus voltage will change here. So answer is A. Next one, resistance switching is employed in air blast circuit breakers. This is a direct question. So especially in case of axial blast circuit breakers. So why we are going to use this resistance switching is because to avoid current chopping. So current chopping phenomena. So to avoid current chopping phenomena, we are using resistance switching in between the contacts of a circuit breaker. The next question is, so which material is used in controlling the chain reaction in nuclear reactor? So we will use uranium-235 as a fuel in case of nuclear reactors. So in order to control the chain reaction, so we will use boron rods. We can also call as a control rods. So control rods to control the nuclears. Okay, so we are on the nuclear here. So the answer is boron. So otherwise generally you can observe thorium, uranium, beryllium are the radioactive materials. So boron is a non-radioactive material. So from that also you can choose the answer. Next question. The next question will be the concept of an electrically short, medium and the long transmission lines is a primarily based on. So primarily, first one is the first primarily based on its wavelength of the line. So if this option is not present, then physical length of the line is the second option. So you should choose this wavelength of the line. Suppose if the wavelength is less than 4000 means we can call them as a short transmission line. So in between 4K to 12K we can call them that as medium transmission line. So more than 12K means we can call them as long transmission line. Okay, so all are having units heads. So heads here and heads here. So wavelength of the line. So sorry here. So it is 4K heads kilometer. So heads kilometer. Units are heads kilometer. So 4000 heads kilometer means we can call this short transmission line. So 4000 to 12,000 heads kilometer means we can call them as medium transmission line, and 12,000 heads kilometer means we can call them as long transmission line. The next question will be the bias differential relay. The bias is defined as the ratio of the number of turns of restraining coil to operating coil. So if we take any protection of generator winding, so there are CTs to the left and right of this winding here. So let me take the CT1 here, CT2 here. So the CTs are connected like this. So the currents entering here is, let me take, it is I2 and here it is I1. So in between we are having the winding called operating winding, so which is having a number of turns of N0. So N0, and here we are having restraining coil. So restraining coil here, let me correct it here. So this is from here to here, okay, and this is restraining coil, which is divided into two parts here, NR by 2 and NR by 2 here. So the biasing differential relay K is defined as, so K is equal to, it's a ratio of NR by restraining coil NR by N naught. So this is the restraining coil and this is the operating coil here. The next question here is, out of the following power plants, what are the base load power plants? So base load power plants, generally if you take the power load curve here, so here's a power here and we take duration here in hours. So there are not edges, it's in hours. Okay, so power duration curve. If you take here, there are two different loads here. The first one is, we can call them as a base load, and second one is, it's increasing like this something. So we can call them as a peak load. These are the two loads here. The first thing is, if we want this kind of base load here. So we want means whatever the power available, we will use this one. Suppose for example, if the river is flowing here, so if the river is flowing means we will use that power to generate hydro electricity. Okay, suppose in a pumped storage power plant, what we will do is the whatever the water coming, we'll pump it back and we can use as a peak load power plant. So whatever the power we are available continuously, we can use as a base load power plant. So in the giving options, whatever the run of river power plant, so whatever the power flowing to the river continuously, we can use as a base load power plant for production of electricity. And similarly nuclear also. So nuclear also we cannot play with the fission. So nuclear fission we cannot play. So once it started means we have to continuously use the power. So among the given options, nuclear and runoff river power plants are the baseload power plants. We can use the pumped storage power plant and diesel as a peak load power plants. So the option is 1 and 2. So option A here is the right option for this question. Next question. For a fixed value of complex power flow in transmission lines having sending end voltage V, the real power losses will be proportional to. So real power losses will be is always because of resistor here, I square R. So here the given question is complex power. So S is nothing but it's a product of V into I. So we can say I is nothing but S by V. So we substitute in this case formula here. So P is proportional to I is nothing but so 1 by V square. That means the power losses is inversely proportional to the square of the voltage. So that is the reason why if we have more and more voltages, the power losses will be less. So this is the reason why we are going for HV AC transmission lines, HV DC transmission lines. So this is the reason. So 1 by V square here. Next question. The next question. The power is transferred from A to B by a HVDC link as shown in figure. If the line voltages VAB is here and VCD indicated in the figure below. So I, that is inverter, is greater than output greater than rectifier here. I greater than O is given here. Now the simple logic here is there is no need to discuss in detail about the converters, rectifiers, etc. Simple logic here is the voltage VAB is here, the power flow is here. So power is always flows from this higher potential to lower potential. So first option is the VAB should be greater than VCD. This is the first option. So check here. So VAB, we are having two options here. And second one is in order to power flow here, so VAB should be greater than 0, should not be negative. Once what will happen, negative means, so negative means the power is flowing from this source to load to source here. So load to source means it acts as an inverter operation, but the given question here is it is rectifier. So always the power flows from this kind to this kind here. So VAB should be greater than 0, should not be negative. So for rectifier operation. Similarly, so VCD should be greater than 0 in order to perform inverter operation here. So the option here is C is the right answer. Next question is, consider a two bus connected by an impedance of 0.05 ohms. The bus 1 voltage is 100 at an angle 30 degrees and the bus 2 is at an angle 100 and at an angle 0 degrees. The real and the reactive powers supplied by bus 1 respectively. So the formula here we are going to use here is, so P supplied power is nothing but it is D by B into Vs square into cos beta minus alpha minus Vs Vr by B into cos beta plus delta. Okay, so now what are the values of B and D here? So let's assume it's a short transmission line, so that we can assume it's a short transmission line. So for short transmission line, alpha is 0 and assume A is equal to D is equal to 1. So B is given, how much B is given here? It is 5 units are ohms. So B is a 5 and delta also given, load angle. So delta is how much here? So it is 30 degrees. Now so PS value, what is D by B? So D is nothing but 1. So B is a 5 into supply voltage Vs square. So what is the magnitude of Vs? 100. So 100 whole square into, so cos of, so beta. So beta value is given. What is the value of beta? So beta is nothing but J5 means it is 90 degrees. So cos 90 minus 0. So cos 90 minus 0 means 0, minus supply voltage 100 into 100 divided by B is a 5 into cos of 90 plus 30. So if you solve this entire equation, you will get it as 1000 watts. So similarly, we can go for the reactive power calculations. So what is the reactive power? So QS is equal to same formula again. So T by B Vs square into sine beta minus alpha minus Vs Vr by B into sine beta plus delta here. So already we know 1 by 5 into 100 square into sine 90, that is 1, minus 100 into 100 by 5 into cos 90 plus 30. Sorry, here it is not cos, it is sine. So once we solve this, you will get it as 268 VAR. So the option here is A is the right option for this question. The next question is, keeping in the view of cost and overall effectiveness, the following circuit breakers is best suited for capacitor bank switching, where we have current chopping phenomena. So current chopping. So for them, the best suited circuit breaker is, it is a air blast circuit breaker. The next question is, the Gauss-Seidel load flow method has the following disadvantages. Tick the incorrect statement. So disadvantage. So following disadvantage here. So we should tick the correct. So it is unreliable convergence, a correct statement, and it is a slow convergence. Yes, of course, is a correct statement. Choice of slack bus affects the convergence. Yes, of course. A good initial guess for the voltage is essential for convergence. Yes, so this is the incorrect statement here. So a good initial guess for the voltage is essential for convergence is a wrong. So we can make the convergence faster if we have initial good guess. So if your guessing is good, you can give faster convergence. Okay, so next question. So the rating voltage of three-phase power system, so P is equal to, so VL into IL. So this three-phase means we can consider say 3 here. So this line to line voltage is a RMS line to line voltage. So answer is RMS line to line voltage is a three-phase power here. So thank you friends, thanks for watching my video. Have a nice day.